So we've talked about weighing galaxies, mapping the galaxy. The really cool thing about the Milky Way and other spiral galaxies are in fact those spiral arms. And so we look at the spiral galaxy, we get all these spiral arms, and then we realize something's weird about this. Because if the stars in the inner part of the galaxy are going faster than the stars in the outer part, the spiral arms should wind themselves up and eventually be ripped apart. So spiral arms should be a very, very temporary and transient thing in a spiral galaxy, if that's the case. And if so, spiral galaxies should be pretty rare, except we see a lot of spiral galaxies. So that means that something else is going on. So why do some galaxies have spiral arms and others don't? And how do you form these spiral arms? Uh, because they apparently are very, very common and very easy to form. A clue comes from looking at two types of spiral galaxies. We have the so-called grand design spirals, and we have flocculent spirals. The grand design spirals are the really pretty ones. Those are the ones you see in the pictures all the time. They are these beautiful spiral pinwheel looking galaxies. Flocculent spirals are just kind of a mess. I mean, they're spirally, but they're not very pretty. And so how does this happen? Well, does something take a grand design spiral and mess it up to make it flocculent? Or do you get a flocculent spiral which something happens to it to make it all get organized into a grand design? Or are these two types of galaxies formed in entirely different ways? So we have to stop and think. Turns out there's actually two ways that theorists have come up with for how spiral arms can form in a galaxy. There's something called self-propagating star formation and something called spiral density waves. Self-propagating star formation was not really the first one proposed, but it seems to explain flocculent spirals. So what would happen is you would have a galaxy and some weird thing happens in the middle and you start making stars. And then what happens is some of those stars explode, and when they do, they create more stars. And then those stars explode, creating more stars further out. But since the inner part of the galaxy rotates faster, then what happens is the stars further out get lagging further and further behind, and you end up with a sort of messy, sort of spiral type thing occurring. And so that would possibly explain where flocculent spirals come from. Another idea was originally proposed somewhat earlier in the 1940s, but by the 1960s was substantially improved upon, was spiral density waves. And the way that spiral density waves work is to realize that in the spirals, that if you somehow stretch a galaxy so that instead of being spherical and all the gas moving around in circular orbits, you stretch it a little bit so it's not really round, then the inner orbits are going to precess. These orbits always these orbits always follow kind of a spirograph type pattern, so they'll precess. And so what will happen is that the orbits in close will precess more than the next ones, which precess more than the next ones, which precess more than the next ones, which precess more than the next ones. And so if all these things are precessing a little bit, you end up with the orbits all clumping up in places. Well, if things are going around in the orbits, where the orbits clump up, then you would exceed the Jeans criterion. If the interstellar medium is moving around in orbits, you exceed the Jeans criterion, and then what would happen is that you would end up bunching up the interstellar medium and then making stars in there. And then that would give you a couple of really nice, pretty spiral arms. Most grand design spirals actually have two spiral arms. And again, that matches this idea right here. An example of this would be like a traffic jam. So you can imagine that you've got a slow vehicle moving along, and then all the other cars are bunching up behind it. And so they're trying to go around, and so you end up with a traffic jam right here. Well, even though this vehicle's moving, the traffic jam is coming in here. Now, if there's going to be an accident, it'll be somebody not paying attention and running into a car in the back of the traffic jam. And so that would be like star formation. When the interstellar medium runs into each other, you would make stars kind of right here when you first run into this. And the front end of the spiral arm keeps moving, but all the interstellar medium is running into the back end of the spiral arm, and that's triggering stars. Now the cars are going faster than the obstruction, so that means that the interstellar medium is going into the spiral arm and leaving the spiral arm. So this would be what we call a density wave. Another example would be if you imagine a car, you have a highway here, and a car pulls over. It's not even blocking the road, but it's changing a tire. Okay, so you have a flat tire. Everybody else is driving on. They slow down and they look. Well, when this car is done, it drives off, but you still have a traffic jam here. And so the cars at the front of the traffic jam start driving off, but cars coming in the back can't get through because traffic is slow in here. So what happens is, long after whatever made the traffic jam, the accident or a disabled vehicle or whatever has gone, the traffic remains, and it keeps building on the back end of it as more cars are running into the back of the traffic jam before the front end goes away. And so again, this is an example of a density wave. Spiral density waves can form in a galaxy, and as the stars are going around interstellar medium, it's bunching up on the back side of the spiral arms. And when you bunch up on the back side of the spiral arms, you start the process of star formation. Then the stars form kind of in the middle of the arm, and by the time you get to the front of the arm, then the stars are already formed, and you just have star clusters. And so that gives you the structure of a spiral arm. So you have a spiral density wave. The actual stars are going around much faster than the arms move. And so the arms are moving at a much different speed than the stars themselves in the galaxy are moving. This is why the spiral arms are more stable than you would expect from differential rotation, which should rip them apart. In fact, the differential rotation is kind of what makes the spiral arms in the first place, is that the inner parts go around in less time, which means that you get more precession, which then starts the whole process of creating the spiral arms. And so that gives rise to density waves. And so now the question is, what can actually stretch a galaxy to start this whole process? And it has something with a lot of gravity. Well, that'd be another galaxy. M51 on the right over here, there's a satellite galaxy here that's colliding with it, and the gravity of the satellite galaxy has stretched M51, and it gives you this classic, beautiful, grand design spiral right there. The Andromeda galaxy on the left over here turns out had a couple of big companion galaxies here whose gravity have tugged on it a little bit, and they probably had an impact. There's another galaxy off to the side here, out of the field of view, that also whose gravity can interact with it. And so that's another grand design spiral. Okay, so we have two different modes of star formation. We have spiral density waves. This actually probably explains where grand design spirals come from. Self-propagating star formation, that probably explains flocculent spirals. And so these two different modalities of star formation are why you get two different kinds of spiral galaxies. And so this kind of explains the spiral arms. And that's just a really pretty picture there of a galaxy with spiral arms, and so I just kind of like to end with that. So NGC 4622 is a very pretty galaxy with spiral arms, and so we will end with that.